Greetings and namaskar to each one who came here to watch this video. In this video, we are going to study indeterministic nature of the microphysical world. Let's first talk about the macroscopic particles. What are they? That can be seen by naked eyes. So not strictly, but yes, they are deterministic. How? This is because we can measure their position, acceleration, momentum, time, speed, etc. Here we can apply Newton's law to understand the macrophysical world. But as we move to the microphysical world, it failed. We can't determine its position, momentum at any instant of time. Thus, microphysical world has the indeterministic nature. Well, as we had gone through double slit experiment in our previous videos, we observed interference pattern, which indicates that electron display both particle and wave properties. We have seen in double slit experiment that it is impossible to trace the motion of electron. Hence, the microphysical world is indeterministic. We can neither follow a microscopic particle along its motion, nor we can determine its path. Such result inspired Heisenberg to postulate uncertainty principle and Max Born to introduce the probabilistic interpretation of quantum mechanics. So this video is further divided into two parts. Number 1, Heisenberg uncertainty principle, and number 2, probabilistic interpretation. Now, taking Heisenberg's uncertainty principle first, let's take a system. Now, according to classical physics, we can exactly calculate its future path if its initial condition is given and a force is acting on it. For example, let's take a particle whose position is r0 and its velocity is v0. All forces acting on it are known. Then, with the help of the Newton's law, we can determine its position and velocity with respect to time. So here, we are able to predict future behavior completely. Thus, classical physics is deterministic. And now, since we know that in quantum physics, we represent a particle by a wave function, psi. And this wave function is actually a spread over a space like this. Why it is considered to be spread? This is so because we saw in double slit experiment that it is impossible to determine the exact position of electron, so it cannot be localized in this space. That's why we take spread region to show area where electron may present. Now, like classical physics, we can't calculate exact position and momentum or a unique path of a particle. And here comes Heisenberg uncertainty principle in rise. You must be familiar with its statement. It states that it is not possible to measure position and momentum simultaneously with arbitrary accuracy. Del x dot del p is greater than or equal to h upon 4 pi, where del x is the uncertainty in position, del p is uncertainty in momentum, h is the Planck's constant having this value. This is a general form of Heisenberg uncertainty principle. Well, this principle indicates that it is possible to measure the momentum and the position accurately, but not simultaneously with accuracy. We can't measure position without disturbing momentum and vice versa, as they are inversely proportional. So more you know about position, the less you know about its momentum. And the less you know about its position, the more you know about its momentum. So suppose if a particle is localized at position, say del x, then there would be del px amount of uncertainty in its momentum. As all quantum phenomena are described by waves, so the uncertainty relation for position and momentum in three-dimension form can be written as del x dot del px is greater than n equals to h cross upon 2. Del y dot del py is greater than n equals to h cross upon 2. And del z dot del pz is greater than n equals to h cross by 2, where h cross by 2 is equals to h upon 4 pi. It is a reduced form of Planck's constant. Here, position and momentum are the pair of two complementary variables. Similarly, Heisenberg uncertainty principle is applicable on another complementary pair, and that is energy and time uncertainty relation, written as del E dot del T is greater than n equals to h cross by 2. Now, let's move to the second part, and that is probabilistic interpretation. In quantum mechanics, we describe state of a particle by wave function psi, the function of r and t. It describes the wave property of a particle. And as we discussed earlier, that psi mod square is the intensity. It is the probability of finding electrons in particular region. Bohr interpreted that psi mod square as probability density. And he gave us equation, that is psi the function of RT mod square d cube I is equals to dp function of r and t, particle at time t, where dp is the probability of finding the particle at time t in volume element d cubed r, which is in the 3D form. Now if we integrate both sides over entire space, we'll get p, which is probability, and we know that probability is always 1. Thus, the total probability of finding the particle somewhere in the space must be equal to 1. So here we end up with the 2 points, Heisenberg uncertainty principle and probabilistic interpretation, which tells us the indeterministic nature of microphysical world. Hope you found this video productive. Thanks for giving your time here. Take care.